good from bad science, and all science uses models. Good science uses models or theories. Same thing in my terminology. And bad science uses models too or theories. We need to understand what a model is. So let's do a little of that today. Let's just try to decide or describe what a model is so that we have an understanding at a very high sort of philosophical level of what a model is. Now, before I get to exactly what models are in science, it's best to know and to never forget this. All is in all is in every, all is in without exception. All models only say what they are told to say. Models, then, are lists of statements of the form, if this, then that. If this, then that. No matter how large models grow, or how sophisticated, or how mathematical, or how computerized, or how much data that's put into them, or from what sources, their natures are not altered. They are always just lists of if this, then that. If this, then that. Now, this applies, as I said, to all models. It doesn't matter what name those models are given or theories. Artificial intelligence, statistical models, probability models, physical models of all kinds, meteorological, air transport models, crop production models, chemical models, sociological models, medical, psychological models, genetic, algorithm models, quantum mechanical, machine learning, everything. All models, on and on. All are the same in essence. All models in every field have the same nature. And all say, all of them, no exceptions, say just what they are told to say and nothing more. Now, this is not a limitation or a flaw. It's just the way things are. Okay. It sounds like a criticism. It's not a criticism. It's just the way models are. All models only say what we tell them to say. Now, here's a let me just give you an example. Here's a simple, common, very useful model, and it's used by casinos the world over. Here's the model. I'm going to quote it to you. If this die has 6 sides, then the probability any side is up in a throw is 1 in 6. Now, that's a model. It doesn't say anything about the actual die besides that it has 6 sides. It doesn't give anything about the physical characteristics or the way it's tossed and the gravity in the room, the slipperiness of the surface on which it hits, friction coefficient, I mean to say, the moisture that's on the hand of the person throwing it, on and on with the innumerable sort of physical variables. No, this is a model. This is a model. The model says exactly what we want it to say and only what we told it to say. It's an accurate model too. It matches reality exceedingly well. Indeed, it makes beautiful predictions, especially because casinos keep a watchful eye on the throws. Vast sums of money are made using this model and ones that are very much like it. Of course, we could think about this model more, and we could think about how models actually relate to the physical world in depth another time. We're just going to try to give an overview of what models are right now and not try to get too deep into physical reality itself. We're just talking about models at this point. This particular model, this dice model, says nothing, not a thing, about what causes any side to be up on any toss. All right. Cause, at least the efficient cause, cannot be inferred from examining this model. This efficient cause was, no cause was built into the model except for a little bit about what we might call the material cause or the form. Not even that. We have all we really know about the thing is it has 6 sides. That's part of the cause. That's part of the form of this object has 6 sides. So that's part of the cause, but it's not the efficient cause. None of the if this then that statements, the model statements, and there's only one, mentioned cause beyond the form of the thing itself. But the model's still very good. So we conclude models can be good, great even, and useful, but absolutely silent on cause. Well, it turns out the opposite's also true. A model can perform well in practice, but we cannot, from that good performance, conclude it has identified the cause of anything. Ensuring cause has been identified is a much more difficult task, as anybody who has painfully designed some experiment only for it to go, incomprehensibly wrong can attest. So since all models only say what they're told to say, we can always, always create a model to say anything we want. All right, simple as that. We can have the model speak in the complex language of mathematics or physics, or we can have it discourse in arcane, computer code, or we can have it project into pictures or words or numbers, whatever we like. We have the complete freedom to make any model say anything we want. Again, that's not a limitation or a criticism. It's just the way things are. We have the freedom, of course, to specify all of the if-this parts of the model, from which we sometimes can deduce and sometimes must guess the then-that parts. We have if this, then that. Well, sometimes we get the whole package at once. Sometimes we can deduce the then-that thing, assuming the if-this parts, or we can work backward, starting from desirable then-that, and we pick compatible if-this parts. So we have the complete freedom to say which and how much and from where the data that goes into the model. And what if this, then that, this data is married to. We have freedom to embrace any simplifications or approximations we want. We can, and an increasing minority even do, cheat. That's part of the replication crisis that we hear so much about too, cheating. In short, we have complete freedom over all aspects of the model. All right. This freedom, of course, comes with a cost, a big cost. Since any model can be made to say anything at all, and anybody can create one, it means models can't be trusted until they are thoroughly tested against reality. That's just a fact that flows from the complete freedom we have in models. Models certainly, absolutely cannot be trusted because of the authority of who builds or rather creates them. That's the fallacy. That's the old appeal to authority fallacy. And models can't be trusted because we need to do something and there is nothing else but this model. That is also a fallacy. That's the do something fallacy. There are always other options. No model has to be used because you have nothing else. That's always BS. Models can only be believed when they're tested independent of the information used to create them. And independent of the people being what they are, independent of the people who created them. If a model only works, of course, which is often seen to be the case by those who created it or it only works built using the information controlled by its creators, we almost certainly have a case of confirmation bias. I said this a million times. Regular listeners or readers to my blog will know that everybody in science knows what confirmation bias is, but everybody also believes it always happens to the other guy. Again, models must be independently compared with reality to prove themselves. Here's a simple thought experiment to prove why all models must be independently tested if you're not already convinced. So there's this team of eminent engineers, all with many awards, high positions, government grants. They claim to have discovered a new theory that can be used to build a machine to safely transport people, and only people, through space to distant habitable planets. It works by dematerializing you here, and it rematerializes you there on the distant habitable planet. The trip is only one way, though, of course, and unfortunately, because there's no machine on the other side built to the theory's specifications that can send anybody back. Of course, one day, if the machine really does work and enough people can be transported successfully in industrialized civilization, capable of recreating the machine, can grow and build up, and people might someday be able to return. We also can't communicate with people on the distant planet, again, because the machine is only one way, and these planets are thousands of light years away. So, and I want to reemphasize the understanding of my definition that there's no difference between a theory and a model on my definition. Now, given this setup, would you step into this machine and be dematerialized, as you've seen other people go before you and be dematerialized? Or will you first demand some kind of proof the machine works? That is, proof that the model matches reality. Or are you going to take the creator's word for it and be convinced by their impressive demonstrations of math and science and their grant dollar amounts and their insistence? Most of their colleagues, 97%, agree with them. Well, if so, safe journey. Now, even though it might not look like it, especially to non-mathematicians or non-coders, it is simplicity itself to create a complex model. Uh, Not that hard work doesn't go into these things, and a lot of models don't require great, vast amounts of thought, but anybody can create a model, even a complex model. It's not that difficult. An enormous list of equations, all accurate in themselves, can be written down with very little trouble. And even with greater ease, we could say those equations apply to some physical thing, some measurable aspect of reality. And that's what we have when we're talking about science, a measurable aspect of reality. For it's we who say that the X, we'll just call it X, something X in our model, means, I don't know, quantity of ammonia or temperature or crop yield or income or whatever it is. It's we who say all those fancy calculations mean if this, then X does that. This is just always, no exception, raw assertion. The assertion may have any number of good and even excellent reasons for believing it, or at least putting confidence in it, but the assertion about X cannot be believed finally until the model proves itself. We must always remember the math and complex systems inside a model are just that. They're just math and symbols. They're just, lifeless symbols. They only take meaning when we assign it to them. They have no meaning in themselves. Although you're likely tired of hearing it by now, what this means is that the only true test of a model is when we witness its boasts about those symbols. Testing a model, now that's what we really want to do here, is we want to test a model. It's not easy. If the model says, if this set of conditions hold, then X does that. And we got two choices. We either wait until that set of conditions arises and then we examine X, or we carefully as possible design an experiment to bring about those conditions. Well, that takes time. Is costly, particularly since we can't test the model on the data we've already collected. We have to test it on new data. This is why this step is usually skipped. Instead, something like certainty of the model's if this, then that statements pertaining maybe to the model's inner coherence, they're offered as proof enough of the model's worth. But that just doesn't work. Look, an ideal model is one which makes perfect predictions. This happens when every one of its if this, then that statements is true in itself and can be proved true, where that every is strict as can be, and where the complete cause of X is within that list of statements. We can't just have a list of true statements. They have to pertain to the X and demarcate its cause, its full cause. Since its cause in all aspects, I mean to say. Since every if this, then that statement in a model is true, this kind of model is true, and we know we have the complete cause built into it, well, this model must predict perfectly. Useful predictions, which are not perfect predictions, can also happen when not every if this, then that statement is true. That is, when some of them are false or uncertain, or even when they are true, but we don't know the complete cause. That applies to the dice throwing example above. The model statements were true, but we don't have the cause. So we only have a model that predicts probabilistically, but it's a darn useful model. Usefulness, of course, is a subjective criteria. It's not a scientific criteria. I want to emphasize that as strongly as possible. It is a subjective criteria, but that it's subjective is not necessarily a shortcoming. A model can be useful to one guy, but useless to another. The same model. It depends on what uses the model will be put. For an extreme example, just as an extreme example, a model that's wrong all the time can be very useful to the man who successfully markets and sells the model. All right. We see this on the stock market and other places all the time. Whereas the model will have no value to those who buy it and actually use it to predict the thing the model is said to predict. This is why, again, you're tired of hearing this, buyers must insist on independent demonstrations of model performance. Well, of course, the more complex a model grows, the more difficult it is to witness enough for all of the situations envisioned by the models, or the model, I should say. Think about a psychic with her internal mind model. She claims to be able to guess if you're thinking of an odd or an even number. All right, you think of odd. She predicted odd, a success. Is her model correct? Does she really have psychic powers? Is her model true? Well, maybe. But one test is clearly insufficient to tell. And even if she guessed right a large number of times, we would still not have decisive evidence her model is correct. Winning poker players know why. Very easily a cause other than that asserted by the model, which is psychic ability, might also account for good results, like the person's giving away a tell or cheating or any number of things. This is why testing models against reality is just so difficult. Even good results can fool you. Again, the difficulty only grows with the model's complexity. A model of guessing odd or even numbers is trivial, of course, but a model which purports to say what the temperature or the level of some atmospheric chemical will be a decade hence is hideously elaborate, and therefore almost impossible to test thoroughly. The more sophisticated the model, the greater number of its if this, then that statements. For testing, a compromise is always in limiting that set to something manageable. With that compromise, of course, should come an increasing uncertainty of the model's value, even after it's tested, because we can't test the model everywhere. It should never be wholly trusted. I hope you agree with that. Sometimes, though, something very like the opposite is true in practice. More complex models are trusted more, even when they're imperfectly tested. And why? Well, we have to consider that those who created these complex models love those models. And why not? Creators spend vast quantities of time and energy and honest sweat in designing, shaping, and polishing these models, like Pygmalion adoring his statue. Their models are beautiful creations, at least in their eyes. The people involved in these large modeling efforts are intelligent, even highly intelligent. We're discounting cheating, which is not that common, but happens usually by lone scientists. But these joint efforts are usually, the cheating is not usually there. It's there, but it's always an affront to cast doubt on their work. It's a kind of an insult. Nobody likes to be suspected of error, least of all those who believe themselves are best thinkers. Harsh questions that could be asked about a model are, for this reason, often not asked, and that's a shame. And of course, as mentioned above, the cost and time required to do robust testing balloon with model complexity. When model users feel that model-based decisions have to be made, and perhaps the funds and the will to do so are low, the temptation to bypass the necessary independent testing is often not resisted. And even when it is not resisted, the temptation with independent testing to resort to shortcuts is too often taken. Certain mistakes in verification creep in unnoticed. Suppose we have a model that predicts the atmospheric deposition of something. An independent test is done, as is proper. Many points never before used in building the model in any way are predicted. These predictions turn out to be good. All right, a success, with good defined by the decisions, of course, that the model users make, and the gains and losses they experience with the model. Now, if we made a quick judgment, a verification judgment, comparing the averages of the predictions and the observation, it appears to say the model is fine. Those averages look close enough, near equivalent. But if we look deeper into it, we see that the majority of points tested were of trivial size. It just turns out concentrations of this atmospheric component that no one really cares about, because these are what happened to happen in the bulk of observations taken during the test. These small amounts are what happened in the world. So a complete look then, digging in deeper, using better measures than just comparing averages, reveals larger values of depositions, the ones really important to model users, are not predicted well at all. Indeed, the error in the model is seen to grow as the value of the deposition grows. Well, that means we have to do the independent tests at points where important decisions would be made by model users. We can't rely on simple tests of goodness, because it might easily turn out that any model would have done well, and we just happen to test ours. And that finally brings us to the idea of skill. I know this is long and complex, but models are not so easy. So this is the idea of skill. I think it's very simple to grasp, although some people have problem with it. Let me know what you think by contacting me. If you don't get this, I really want to make sure everybody has a good grasp of this. Suppose we had a good guess of the average values of deposition over a time period of interest to model users. Maybe the mean of old observations were taken. We could use that average and use it as if it were a model itself. We can make predictions with it, just as we can with any model. All the predictions happen to be the same value, which is just the old average, but it's still a model. It's still a prediction. Now, the deposition model we were looking at a moment ago, the sophisticated one, it's physically and chemically accurate, or so claim its creators. It appears to explain the physics and chemistry and other components of the atmosphere in a satisfying way. Lots of peer-reviewed papers were written saying so. A large group of important users further implement this model. Much is invested in it, not just by the modelers, but by, say, politicians and other groups. Important decisions are made using it. Lawmakers embrace the model and require it to be used. But then suppose we compare that sophisticated model to that average model, that simple, trivial average model, and the average model beats the sophisticated model using the very verification measures we thought important. Which model is better? Well, it's not a trick question. We just said it, the average model. The sophisticated model does not have skill. Skill is a technical term. It does not have skill with respect to the average model. Since we'd be better off using the average model, we should not use the sophisticated model, no matter how important it was thought to be, or how much is invested in it, or how official it is, or even because it's believed the sophisticated model explains the physics and chemistry and so forth better than the average model. In truth, the sophisticated model, because it cannot and did not beat the simple average model, cannot explain the physics better. How could it? It can only appear that way to those who love the model, because if it did explain the physics better, it would have made better predictions. It's as simple as that, dear listener. And the final lesson is just as simple. Put all models to the test, all of them, each and every one. Thank you for listening.